Alright students, welcome to part 2 of our special topics lecture videos designed to help you guys with your standardized exams and your general organic chemistry concept understanding. Now, standardized exams with organic chemistry sections such as the MCAT, DAT, PCAT, and GRE often contain questions that require you to sort molecules in order of increasing or decreasing boiling points. How do we do that? Well, here are a couple of rules. First, you need to remember what you've learned about intermolecular forces. Remember that London, also called van der Waals forces, are the weakest. These occur when there's very little electronegativity difference between the atoms in a molecule, such as carbon and hydrogen. We often see London forces being the most prominent for nonpolar molecules like alkanes and alkenes, such as methane, ethane, propane, or ethene or propene, and so forth. Polar molecules like HCl, which contain atoms with a larger electronegativity difference in them, have higher boiling points. This is because the sustained partial positive and partial negative charge in the atoms of these molecules help those molecules to stick together intermolecularly. Now remember that the stickier molecules are to each other, the more heat it will take to break them apart and hence to boil them off. Thus, they will have a higher boiling point. This type of intermolecular force is called dipole-dipole interaction. Hydrogen bonding is really more like an exaggerated version of dipole-dipole, kind of like extreme dipole-dipole. Hydrogen bonding occurs when a hydrogen atom is bonded to a fluorine, nitrogen, or oxygen, as in water, for example. Hydrogen bonding is caused by the large electronegativity difference between hydrogen and these three atoms, fluorine, nitrogen, and oxygen. Hydrogen bonding is the strongest of all these intermolecular forces. Dipole-dipole is the second strongest, and London forces are the weakest. So if we're asked to sort molecules according to their boiling points, we should keep these intermolecular forces at the forefront of our minds. The stronger the intermolecular forces at work, the more energy will be required to break the molecule apart, turn it into a gas, and hence boil it off. Consequently, the stronger the intermolecular force, the higher the boiling point. Let's take a look at some examples by sorting through this table of molecules that I've personally compiled and identified their intermolecular forces. Once we've done that, let's see if we can take a look at their actual boiling points, just to see if the predicted trends hold. Beginning with our 3-carbon long molecule propane, what intermolecular force does it have? Well, of course, all it has is London forces. By comparison, butane also has London forces. If we go to another 3-atom long chain, this compound, dimethyl ether, what does it have? Well, there's a larger electronegativity difference between carbon and oxygen, so this is dipole-dipole. Similarly, methyl ethyl ether, this compound, also has dipole-dipole. If we move over to these alcohols, they have a hydrogen bonded to an oxygen. This compound, ethanol, will thus have hydrogen bonding as its strongest intermolecular force. This compound, propanol, will also have hydrogen bonding. We move over to these amines. Do they also have hydrogen bonding? Yes, they do, because hydrogen is bonded to nitrogen. Let's see if we can take a look and find trends in boiling points. We would imagine that if we're dealing with compounds that are roughly the same size going across this row, that the boiling points would increase as the intermolecular forces increase. But what as we go down? I've got two molecules that have the same kind of intermolecular forces here, propane and butane. But one of them is bigger. What's that going to do to the boiling point? Let's see. Boiling point of propane, negative 42.1 degrees Celsius. Of butane, negative 0.5. So you can see that if all other things are equal, larger the molecule, the more intermolecular forces are going to have, and thus the higher the boiling point will be. Let's see if this trend holds. Over here I've got dipole-dipole, negative 23.7. A slightly larger molecule with the same interaction, 10.8. Here I've got a similar sized molecule, but it has hydrogen bonding. What does that do to the boiling point? Knocks it all the way up to 78 degrees Celsius. Let's look at this slightly larger hydrogen bonding molecule, 97.4. Now we look over at these molecules. Also, they have hydrogen bonding, so they should have boiling points that are higher than these London forces and dipole-dipole analogs over here. However, how do they compare with the hydrogen bonding neighbors right here with these alcohols? Let's take a look. Boiling point of ethylamine, 16.6. Boiling point of propylamine, 47.8. So you notice that hydrogen bonding certainly does make these molecules have a higher boiling point. But why is hydrogen bonding on a nitrogen not as strong as hydrogen bonding on an oxygen? The answer is because nitrogen is less electronegative than oxygen. As a result, the difference in electronegativity between these hydrogens and this nitrogen is less. So there's less of a partial positive and partial negative charge in these amines than there are in these alcohols. I hope that that makes sense to you guys. This is a great table to help illustrate the differences in these intermolecular forces. One thing to which I just alluded is the following. If you have all other factors the same, that is, if all other things are equal, I've got molecule A and molecule B, and they both have the same intermolecular forces. Generally speaking, the larger the molecule, the higher will be its boiling point. We definitely saw that in the previous slide. Propane had a lower boiling point than butane. Why? Because butane is bigger. Because it's bigger, it will have more London forces than propane. Hence, will require more heat to get it to boil. The other fact is this. Generally speaking, if all other things are the same, that is, if you have two molecules that have the same intermolecular forces, but one has more branching and the other does not, you will see the less branched molecule having a higher boiling point. Why in the world is that the case? Well, imagine I've got a straight chain alkane, and it's floating around a solution with zillions of other molecules of itself. If it's straight chain, it can stack a lot more tightly on top of itself, thus increasing the intermolecular attraction between those molecules and making it harder to boil them off. Now imagine I have an alkane that has branches in it. Because it's branchier, it's not going to be able to stack as tightly. Thus, it's going to have a lower boiling point. Let's take a look at some examples. What is the correct order of boiling points for the following isomeric compounds? Which of the following amines has the highest boiling point? Now here's an example where what I have is the same type of intermolecular force at work. The only difference is the size. The last question, which of the following amines has the highest boiling point? This is a little different. Here I've got a tertiary amine. Is there any hydrogen bonding in that? Here I've got a primary amine. Is there any hydrogen bonding in that? And here I've got a secondary amine. Is there any hydrogen bonding in that? And how much? How will that affect the boiling points? I'll let you decide, and we'll get to it together in class. We now move on to the wondrous topic of sorting molecules according to their acidities. Acidity can be described in a few different ways. In the context of standardized exams, acidity is simply a reflection or a measure of how easily a proton, that is an H+, can be removed from a molecule. Now I like to think of this as being kind of like a tug of war. Let's pretend that these three guys over here are playing tug of war with this little guy over here. These three guys represent the rest of the acidic molecule in question. This little guy represents an acidic hydrogen who's holding on to the rope in the tug of war game with only one hand. You can see, with his free hand, he's waving at us. Now along comes a big bad base. Because these guys in the molecule right here are pulling on the rope away from the hydrogen, I'm indicating that with these little arrows here. The hydrogen's grip on this rope is very loose. That means that this hydrogen is much more acidic. So when this base comes and grabs that hydrogen, it's easily able to make him break his grip on the rest of the molecule. That gives us this. Oh, and all of these other guys over here are very sad because they lost their hydrogen. Now the base walks away with his hydrogen in hand. Now this scenario kind of looks like one that we'd see in a molecule like this, where these three electronegative fluorines are pulling electronegatively electron density away from the rest of the molecule. That makes this hydrogen right here much more exposed and loose in its grip on this oxygen. Hence, this hydrogen's more acidic. This makes it so that a base can easily remove that hydrogen. Does that make sense? You have guys who are pulling electronegatively away from a hydrogen. It makes the hydrogen more acidic. Now let's imagine an alternative scenario in which the rest of the molecule is made up by guys like this. Now do you see what I'm saying? These guys aren't even really trying. They're lazy. Now, because they aren't pulling the rope, the hydrogen's grip here on the rope is not going to be loosened as much. Therefore, this base has to work a little bit harder to remove this hydrogen. Hence, this kind of hydrogen is less acidic. Now, this kind of scenario is the one that we'd see in a molecule like this, where there are no electronegative withdrawing groups over here. Now, don't get me wrong, this carboxylic acid still is acidic because the resulting electrons will go in here and be resonance stabilized between these two oxygens. But it's definitely not as acidic as the previous example, which has 3 fluorine atoms that are sucking electron density through the molecule and loosening the hydrogen's grip here. Thus, this hydrogen will be less acidic, and this base will have to work a little bit harder to remove it. Now let's contrast this with an example like this one, where these guys are actually pushing the rope toward the hydrogen. Now I realize that this would be a slightly ridiculous example in real life, but I'm using this only as a metaphorical analogy here. So I want you guys to imagine hypothetically that we're playing tug-of-war and these guys can actually push the rope toward the hydrogen. How is that going to affect the hydrogen's grip on the rope? Well, what it's going to do is it's actually going to increase the hydrogen's grip on this rope and decrease its acidity. Thus, in this type of scenario, the base is going to have a super difficult time removing this hydrogen. This is a hydrogen that is much less acidic than the previous 2 examples. Now this scenario is the kind of scenario where we would see a molecule like this. Now you can see that this hydrogen right here is somewhat acidic, but over here I've got an electron donating group. This oxygen actually pushes electron density by resonance, by thrusting its lone pairs into here. So this is kind of like this tug-of-war where the guys are pushing toward the hydrogen. That actually strengthens the hydrogen's grip on this oxygen and makes this hydrogen much less acidic than it would be if there were an electron withdrawing group over here. Thus the base can come in, but he has to have a lot more reactivity to be able to remove this hydrogen than he would for analogous examples where there was an electron withdrawing group. And that gives us to gets us to the most important take-home message from this piece. Remember that withdrawing groups in molecules increase acidity, and donating groups decrease acidity. So let's apply this to some actual molecules. How do you think the added halogen atoms over here in these carboxylic acids will affect the acidities of these hydrogens that I've circled? Will they decrease them, increase them, compared to this one that has no halogens? And more importantly, can you sort these compounds from least acidic to most acidic? I'm not going to give you the answer, of course, but I want you to see if you can come up with the answer on your own. Let's take a look at some sample standardized exam questions. Question number 1. Although there are known inhibitors of the citric acid cycle, the pH of the mitochondrial matrix can alter the charges of various carboxylic acids, which may have an effect on the rate of the reactions taking place within the cycle. Which of the following pairs does not describe their relative acidities? Now, I should mention here, after reading that question, that this seems to be a common practice in standardized exams. That is, to have a long paragraph with lots of words here that are completely irrelevant and don't contribute in any way to you being able to answer the question. This particular example is one in which if they had just had the last sentence here, the question, it would have been good enough for you to answer it. But they want to confuse you a little bit, so they baffle you with lots of words up here that you really don't need to read in order to answer the question. When I read this kind of question, I actually skip all of this stuff and go straight to the question and ask myself, is this a question that I can answer without reading all of this crap before it? In this particular example, the answer is yes, it is. So when I reread this, I read this as blah, 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 bling, bling, blah, blah, who gives a freaking crap? And then I get to the question, which of the following pairs does not describe their relative acidities? In other words, they're asking you to sort through these options and choose which of these options is incorrect. Let's take a look at another example. Which of the following molecules will be the least acidic? Now there's an example that's a little bit more short and to the point. We often see standardized exams asking questions about this term called degrees of unsaturation. What in the world does that mean? Well, here's my answer. If you have a straight chain alkane, you might remember that its general formula is CnH2n plus 2. Now, you might not believe me on this, but if we throw a couple of examples at you, I bet you could figure this out pretty quick. Here are two different compounds. They're isomers of each other. Well, let's see what their formulas are. If I count carbons and hydrogens, you'll see that both of these have the same formula, C4H10, which indeed is consistent with this general formula for alkanes, CnH2n plus 2. So you can see that the amount of branching doesn't change the formula of an alkane. So what does change the formula of an alkane? Well, let's see what happens if I insert a ring. So over here we saw some 4-carbon long molecules. Here's a 4-carbon long molecule, except now it's a ring. What does that do to the formula? Well, the overall formula is now C4H8. So if you compare the formulas by inserting a ring, I've actually decreased the general formula to CnH2n. So I've decreased it by 2 hydrogen atoms. Similar thing can be seen here in this 5-membered ring. If we insert a ring, it decreases the number of hydrogens by 2. Now what if I insert a double bond? I insert a double bond, we count hydrogens and compare them with these their saturated analogs up here. You'll see it does the exact same thing as inserting a ring. The overall formula is C4H8 if I throw in a double bond. Guess what would happen if I threw in a triple bond? Yes, the number of hydrogens would go down by 2 more. Thus we can see that if I insert a ring, it decreases the overall number of hydrogens by 2. If I insert a double bond, it increases the total number of hydrogens by 2. Does that make sense? If I change that double bond to a triple bond, it decreases it by another 2. What if I do both? So here's a ring. This is an extremely unstable ring, but let's take a look at it for the sake of just learning. Here I have a ring that also has a double bond in it. What's the overall formula here? It's C4H8 or H6. So you can see I've gone from the general formula for an alkane, and I've not only lost these 2 hydrogens, but I've lost even 2 more. This compound's general formula is CnH2n minus 2. Now one thing I need to tell you is that when we address this subject, each ring or multiple bond is called a degree of unsaturation. So we could say that right here, this molecule has 1 ring, so it has 1 degree of unsaturation. This molecule has 1 double bond, so it has 1 degree of unsaturation. To figure out how many degrees of unsaturation there are, what you need to do is compare a molecule's formula with what its formula would be if it were a full straight-on alkane. You take the difference in the number of hydrogens and divide it by 2. And that is the number of degrees of unsaturation. You got this? Good. Let's go to some questions. How many degrees of unsaturation are there in a compound with the formula C7H12? Once again, to do this, we'd have to figure out what the formula for a carbon or C7 molecule would be if it were a straight chain alkane. What's the difference between that formula and this formula? And how many rings or double bonds would be required in order to go from the general formula to this formula? That's the number of degrees of unsaturation. What is the degree of unsaturation for a molecule with a molecular formula C30H60? Same thing. You just throw in the general formula for an alkane. How many hydrogens would we have if we had 30 carbons in a regular straight chain alkane? What is the difference in the number of hydrogens between that and this number, 60? Take that difference, divide it by 2. That is the number of degrees of unsaturation. Standardized exams also ask sporadic questions about the amount of energy released or consumed in certain chemical processes. Let's consider these examples here. Which of the following molecules produces the most heat per mole when reacted with O2? Now this is one of those reactions you might be scratching your head about and be confused. Please keep in mind that if you take an alkane, as all of these are, and you react it with O2, that kind of reaction is combustion. You're taking an alkane, reacting with O2, and making CO2 and water. Combustion reactions, which are the reactions that fuel our cars, basically convert these molecules into energy. The answer to this question is which of these molecules has the largest number of carbons and hydrogens in it per mole? The answer here is going to be cycloheptane. Let's go to the next question here. For which of the hydrogenation reactions shown to the right will the energy per double bond be most negative? So in these examples right here, what we're doing is we're taking compounds that have double bonds and hydrogenating them to convert them into alkanes. Which of these reactions would be the most negative per double bond? Now this looks like a kind of confusing question, but I really want to reword this. This question, all it's really asking is which of these reactions would give off the most energy. Now remember that negative energy reactions are exothermic. They give off energy. Positive energy reactions are endothermic and consume energy. So when you're asked which of these reactions gives off the most energy, what we're really being asked is which of the starting materials here is the least stable. Okay? Which is the least stable? The least stable one is the one that's going to give off the most energy by going to the right. The most stable one is going to be the one that gives off the least energy as it goes to the right. I'm not going to give you the answer once again, but I'll let you think about it yourself, and we'll talk about it in class. Another family of questions that frequently pops up is those that address issues of comparative solubility. Let's take a look at this one. A chemist hopes to make a medicine less biologically active by preventing its quick absorption through the lumen of the stomach. Which of the following reactions would be a good place to start? And then it has a list of different reactions. Now, in order to answer this question, the first thing we have to ask ourselves is, what is the solvent in the stomach? And the answer is water. Does that make sense? In our bodies, we are composed of a huge percentage of water. Thus, when we're talking about making things more or less soluble in our bodies, what we're talking about is trying to make them more or less soluble in water. So we look at each of these four reactions and ask ourselves, which of these reactions actually make something more or less soluble? In this particular case, this chemist wants to make something less biologically active by making it less soluble, less able to absorb through the lumen of the stomach. So let's take a look at these reactions. Here's an example reaction where I've just taken an alkene and I've hydrogenated it to turn it into an alkane. This is an example that correlates with option number A. Question you need to ask yourself is, does this reaction really change the compound solubility in water a whole heck of a lot? The answer is no, not really. Let's go over here to option B. In option B, we could take a carboxylic acid and reduce it with lithium aluminum hydride, and what it does is it converts it into a primary alcohol. Does that change a compound solubility in water a whole heck of a lot? It actually does a little bit, but that's only if I'm starting with a carboxylic acid. This particular question hasn't specified what functional groups are present in this molecule. So if I were starting with an amide or an ester, the amount of solubility difference might not be that significant. Let's take a look at the third example, converting carboxylic acid into a methyl ester. So this reaction, esterification, is one that you've seen. I can convert a carboxylic acid to an ester. Does this reaction change a compound solubility in water? Heck yes, it does. And this is something I want you guys to remember. Carboxylic acids, generally speaking, are wicked soluble in water. Even if they've got big, long, nonpolar chains, they are very, very often very, very soluble in water. Because of that, a lot of medicines that need to be absorbed quickly into the body have carboxylic acid groups installed on them. But what if I take away this H and replace it with a methyl? Is an ester soluble in water? Not by as much. The difference in solubility is going to be quite significant between these two. So if I were an organic chemist, and I am, trying to decrease a compound's solubility in water, this would be a really, really good way to go. The last one is reacting a molecule with Socyl-2, thionyl chloride. You might remember that this converts an OH to a Cl. Is there a huge difference in solubility between these two? There is a slight difference, but it's not as significant as this. Once again, taking a carboxylic acid, which is wicked soluble in water, and converting it to a methyl ester definitely decreases the solubility overall. So the answer to this question is C. Let's put our expertise to the test by sampling another example question. A crazy chemist needs to separate a mixture containing the 5 molecules shown here. She begins by treating the mixture with warm chloroform water. One of the 5 compounds is soluble in chloroform, which is the organic or non-polar layer. The rest of them go into water. Question: which of these molecules dissolves in chloroform? Now remember, chloroform is an organic solvent, which is a non-polar solvent. So what you're really trying to figure out is which of these guys will go into water and which of them won't. Now if we look over here, we start looking at intermolecular forces. Water, of course, has hydrogen bonding. So molecules that have hydrogen bonding will be more likely to go into water. Acetaminophen has hydrogen bonding here and here. Amantadine has hydrogen bonding up here. This aspirin has a carboxylic acid group up here. This molecule here has an NH2 hydrogen bonding. It is F-enzimide. But caffeine, does it have any significant hydrogen bonding? It doesn't have any at all. What that means is these 4 molecules right here are going to go into water, and caffeine will go into the chloroform. So the answer is D, caffeine. Let's go to the next question. The chemist concentrates the 4 molecules that went into water. So the chemist now has these 4 molecules, evaporates off all of the water. That's what we're saying when we say that the chemist concentrates the 4 molecule. Then she dilutes these 4 molecules in hot ethanol. One of these 4 molecules goes into hot ethanol and the other 3 do not. Which one goes into hot ethanol? So once again, we ask ourselves the question, is ethanol polar or non-polar? Does it have hydrogen bonding or not? It of course has hydrogen bonding. So we have to look at these 4 molecules and ask ourselves, which of these has the most significant hydrogen bonding? Which is the one that's going to go into ethanol the most? Well, caffeine, option B, is obviously out because it was gone in the previous question. So we're looking at acetaminophen, ethenzimide, and amantadine. Which of these guys is the one that has the strongest hydrogen bonding? Acetaminophen has a phenol and an amide. Ethenzimide has an amide. And amantadine has an amine. See this amine here. Which of these guys is going to be the one that has the strongest hydrogen bonding between these 3 options that I'm given? The answer is acetaminophen. The reason is because an OH here has a stronger electronegativity difference than any of these NHs. Hence, I'm going to have a stronger partial positive and partial negative charge. Also, I have 2 groups that have hydrogen bonding in acetaminophen, the OH and the NH, whereas in amantadine I've only got an NH2, and in the ethenzimide I've only got an NH2. It hasn't given me aspirin as one of my options in this question, so I am not going to even consider or worry about that. And now to our last subject, different kinds of isomers. Now here are the different types of isomers defined. First, if we have 2 molecules that have the same molecular formula but a different bonding order, they're called constitutional or sometimes structural isomers. For example, these molecules right here, I wrote 2 molecules, but there's actually 3, all have the formula C6H12. But their individual atoms are bonded together in a different order. Can you see that? So these are all molecules with the same exact formula, but they're just bonded together in a different order. These are constitutional isomers. Stereoisomers can be defined as this. If 2 molecules have the same molecular formula and the same bonding order, but different 3-dimensional shapes, either around a stereocenter or a double bond, then they're called stereoisomers. Now there are two different kinds of these, enantiomers and diastereomers. Here are some examples. You can see that in this group here I've got molecules where the bonding order is identical. This carbon, for example, is bonded to a bromine, a hydrogen, a CH3, and an ethyl. So is this one. So these two molecules have the exact same formula and the exact same bonding order. They are not constitutional isomers. They, however, have a different three-dimensional structure around that stereocenter. And because these two compounds are mirror images of each other, they are enantiomers. Now look at these two molecules. You'll see that they have the exact same bonding pattern, the exact same bonding order. The difference, however, is these stereocenters are different in these two molecules. You'll notice that these two molecules, left and right, are not exactly 100% mirror images of each other. They are mirror images at this stereocenter here and here, but they are not at the other stereocenter. Half enantiomers, or compounds that look like they're enantiomers at some stereocenters but not at others, are diastereomers. They're not full enantiomers, they're somewhere in between. Here's another type of diastereomer. You have two molecules that have alkenes in them. One is an E alkene and one is a Z alkene. Exact same bonding order. This carbon is stuck to CH, or stuck to an H and stuck to a CH3. So is this carbon. The only difference is the three-dimensionality around this alkene carbon-carbon double bond. These are a different kind of diastereomer. The last kind of diastereomer is a cis-trans diastereomer around a ring. Now, one more thing I want to point out is I've seen numerous standardized exams that love to use the term geometric isomer. This term is outdated and should no longer be used, but for some reason exam writers still use it. The term geometric isomer is a synonym with the term cis-trans isomer, which is a specific kind of diastereomer. Please keep in mind that if you stumble upon one of these moronically ignorant questions, that a geometric isomer is a cis-trans isomer. Do you feel good about all this crap? I hope so. Let's prove it by looking at some actual examples. Question number 1. Which of the compounds shown over here to the right are structural or constitutional isomers? Question number 2. Which of the following can exist as geometric isomers? Now remember, this term geometric isomer is an outdated, stupid term that shouldn't be used anymore, but for some reason keeps cropping up on standardized exams. What this question is really asking is which of these compounds can exist as cis-trans isomers? And that ends our first Lecture 1 special topic presentation. I hope that you've had an enjoyable time, and I hope that this has helped you review and re-solidify some concepts in your minds that you should have already learned over the course of your year in organic chemistry. More importantly, I hope that it helps you excel when you hit those standardized exams. Until next time, have a good day.